In this session, we are now going to deal with the frequency calculations over here. So, we are changing our analysis type from now. We are going to deal with the natural frequency calculations. Otherwise, we can say we are going to calculate for the frequencies of that particular system that might be a forced vibration, torsional vibrations, or free vibrations. Depending on our inputs, we are going to calculate for that particularly. So we are having one numerical for that one. So this is our spring assembly. Over here we are having one spring. A mass is placed at the top node. We are having one spring element, one mass element, which we are going to disturb in a vertically up and down fashion. That means we are having an MDOF is written over here. That means master degree of freedom. Once we are getting the MDOF word, means we should go for the reduced as a subtype. So we are having the material properties for this particular numerical as a K value for a spring, a stiffness constant, weight, but we are going to use the value input as a mass. So we should go for the division with respect to the gravity, but the units are given in lb, so we should divide it according to that one. So we need to calculate for the mass and we need to solve this particular numerical. So now we are going to use two different element types than we had used earlier. So one element type goes mass 21. This particularly mass element is known as mass 21, and this particularly a spring element is known as combination 14. So start the procedure for the modal analysis. We can say it is, say preferences. The preferences are structural, and just say OK. Once our preferences are set, now we need to enter for the element type. We are now needing to enter for the new element type, which are mass 21 and combination 14 or 14. So say element type, add over here, and again say add. So we are going to use first for the combination, so come down in a first block over here. So let us see for the combination. We are getting our name as it is over here as a combination. Once we are going for the combination, we should check in opposite block over here. We are having the first option highlighted, spring damper combination. We are going to use for this particular spring element. So just say OK. We are going to add for a combine 14. Otherwise say delete, add it, just say 14 over here and say apply. We are adding for a combine 14. Next is we need to go for a mass element for the natural frequency calculation of this particular system. So we need to put a mass over here at the top node. So we need to define the element type for this particular mass is mass 21. So when we are adding our element type, in the element type itself, the first element type by default indicated over here as a structural mass 3D mass 21. Rather we can go for 21 over here directly and just say OK. Now we are adding our element types for combine 14 and a mass 21. So we need to read our numerical very carefully, because when we are going for the mass values or a mass element type, so we should go for the options of that particularly. So this particular system goes in a two-dimensional cases. We are having an MDOF specified, that means initial displacement, whatever we are placing for the system to get disturbed over here. So when we are going for the MDOF or the master degree of freedom with respect to the mass value, we should check this particular system is 2D or 3D. So this particular system is 2D. Now again one cross check we need to go for, is it having a rotational degrees of freedom or not. So we are going to see over here we are having only one up and down fashion. MDOF is given by these particularly two arrows. One is going up, one is going down along the y-axis specifically mentioned over here. So we are having MDOF written over here. We are not having any kind of a rotational degree of freedom. That's why we are not going to use for that one. So minimize it. Keep it on a mass 21 without forgetting, once we are reading our geometry, we should say options in our element type. Once we are saying option, now here we need to cross check for the rotary inertia options. Over here in a new pop-up window, we need to go for rotary inertia option. Just scroll it down. Now we are knowing it is a 2D numerical. Once we are saying 2D, it comes on a last two options. It is a 2D with rotation and last one is 2D without rotation. So our numerical is not having any kind of a rotary inertia. So we are supposed to use it, the mass in such a fashion which is a 2D mass and it is not having any kind of a rotary motion. So 2D without rotation over here and just say OK once we are setting it. After that, close it, and now we should go for the real constant of this particularly two element types. So add the real constants for this combination 14. So it is a spring element, so we need to add it first because we are defining first element type for the combine 14, rather we can say it is a spring element and just say OK. Whenever we are going to see for a spring element, we should have a stiffness constant value with us, and we are having that one value over here specifically given as 48 lb per inch. So I'm going to enter over here as a 48 in front of that one. Damping coefficient and nonlinear coefficient over here CV1 and CV2 we are not supposed to apply because it is not having any kind of a damper which is attached to this particular system. So it is just a spring constant. So we need to enter for the K value and just say OK. Once we are setting our element type for the combine 14, we need to add for and the mass 21 and just say OK again, keeping it on highlighted mass 21, say OK. It is a 2D mass, so we are supposed to enter our mass value over here. In the numerical we are getting as a weight 2.5 lbs. Now we need to divide that particular weight by a gravity, but due to the considerations of your geometrical inputs, what you are going to actually use as the inches, lbs, newtons, kgs. According to that we need to convert over here and we are dividing our weight value divided by gravity of 386 and whatever the value comes over here is a mass. So mass value we are having 0.006477. So we are supposed to enter for that particular value over here in front of a 2D mass in the second real constant set and just say OK. Now we are entering our two parallelly constant sets over here, for one for combine 14 and another one for mass 21, and just say close this particular window. Once we are closing that particularly, we are not supposed to go for the material properties with respect to the spring element or the combine 14 element, because once we are defining its stiffness constant, we are not supposed to separately define for its another material properties. So K value itself defines its material property. So once our real constant sets are over with respect to the combination 14, we are supposed to go directly with respect to the modeling option. Say modeling. In the modeling, we need to create for a finite element over here, so we can go for and create. It is a one-dimensional case. It's a spring element, so we can directly go for the nodes plotting over here. So it's a spring element. Suppose we are not having any kind of an height constraint, because once we are having a K value, it is not having any kind of an height limitation with respect to the modeling. So we can take it at randomly over here. So minimize over here and just we are going for inactive CS. First I am plotting over here at a 0, 0 and next node I am plotting at a distance of 0.33. We can take it anything 0.33, 1, 2, 3, 4, 5, whatever, and just say OK. Now we are having two elements at a time, two nodes at a time. Now I need to create for two different elements, one from first number to the second number node as a spring element, and another one goes for the second number node only, placing a point load, or we can say it is a mass assigned to this particular node. So we are coming out of our nodes. Just enter into the elements, single click on an element, say auto numbered, but without going for the creation of an element, we should go for the first element attributes. The first option comes in element is element attributes, so single click on that one. Now this is a new pop-up window for us, and without forgetting we should cross check it very carefully. First we are going to create for a combination 14, so we are going to keep it on a combine 14. We are knowing in the real constant set we are defining our stiffness value with respect to the K, with respect to the spring element in a real constant number set 1, so keep it on set 1 and then say OK. Now we can go for the auto numbered from first number to the second number node and just say OK. Now we are having a spring element over here. Now again I need to go for the mass element located at this particular 2 number node. According to this numerical, we need to add our mass at the second number node. So say again auto numbered over here, but without forgetting, before going for the creation, we should go for the element attributes back. In the element attributes, our element type is over here as mass 21 right now. It is a point mass. Now we need to go for the mass value which is assigned in a real constant number set to with respect to that particular element type. So we should suppose to go for real constant set over here as a second one and just say OK. Once we are selecting that one, we should go for auto numbered. Select only single node at a 2 number over here and just say OK. We are creating our spring element and a mass element. We can cross check over here, say plot our elements. You can see the mass over here located at a second number node and a spring element over here. We can go for an again utility menu, plot control, style, size and shape. Switch it on for the size and shape and say OK. We can see this is our spring element having a K0 as a stiffness constant value, and this one is a M0 mass attached to that particular node over here having a mass value. So these are the ways we can cross check the numerical after the modeling.